Alright, Module 2, Transistor. Your bipolar junction transistor, BJT, field effective transistor, FET. Your bipolar junction transfer, positive negative type semiconductor sandwich between two positive type semiconductors, and a negative type semiconductor sandwich between two negative type semiconductors. Its three-terminal naming E emitter, B base, C collector. Both electrons hold responsibility for the current conduction. Some of the bipolar junction transistors during the doping wise emitter is greater than collector greater than base. Two junction emitter base, JEB, and junction collector base. Transistor operation. Junction emitter base is found biased by battery junction EE by depleting energy region decreases the majority carrier flow over the emitter base given the ampere majority over the voltage emitter. Ampere emitter. The voltage center collector base is reversed by over the battery voltage constant current and depletion region with the increase A majority carrier occur over the collector given the current ampere minority. With both battery supplies given the simultaneously hold of the base region during the voltage emitter VE act majority carrier with the cross of the base region to each collector given the current ampere current. So the current over the bipolar junction transistor can be written as amperes E plus ampere IC plus IB, IC plus ampere majority plus ampere minority, ampere capacity equals A times ampere E times ampere CO. A is defined as fractional total emitter current represents holes which are the travel of the emitter across the base collector. ICO is the leakage current. Depending upon the common terminal between the input-output circuit transistor may be the operating three modes of the bipolar junction transistor: common base, common emitter, common collector. Depending on the bias of the junction emitter base and collector base. Transistor 3 region operation: junction emitter base, forward bias, reverse bias, junction collector base, forward bias, reverse bias, region saturation operation, saturation active, current off, application on switch, off switch, input characteristic, plot input current against the input voltage with the output voltage parameter with a particular region operation active. Graph is plotted with the input voltage base, emitter current, ampere emitter, keeping of the voltage with the voltage collection emitter parameter, correcting current variation of the emitter base voltage similar to the forward characteristic of the positive and negative junction diode. However, the increase of the magnitude of the collector by base voltage causes the emitter current to increase for a fixed voltage base emitter because of the effect of the base with the modulation output characteristic of the plot of the output current against the output voltage with the input current as a parameter. The graph is plotted between output voltage with the voltage current base collection base output over the input current and keeping the input current voltage emitter as parameter. Active region. In this region, the junction emitter bias is formed with a junction collection bias, reverse bias. Collector current is independent voltage current bias is depending on the emitter voltage capacity is equal to ampere current is equal to ampere majority plus ampere minority. Ampere current is equal to IECOB. COB is known as ICO, leakage current with a collector with a base leakage. Current with the emitter is open since the current is very small, but the magnitude of ampere current is an ampere emitter current cut off in the region. Here both junctions are reversed by the region of the ampere emitter is equal to 0, character of the cutoff region, and region ampere current is equal to the ampere current base leakage and range of nanoamperes. Saturation region. Here both junction force by the region on the left of the graph where the voltage collector bias slightly positive. The ampere emitter is equal to 0. Give the exponential variation collector current junction collection bias. Forward bias collector positive to respect base, and give the rise of the whole junction current flowing through the collector to base opposite original flow due to the transistor action. Output resistance collector bias is very high because of the very large in collector voltage, very small change in collector current. CB current amplification factor ratio. Output collector current with the input current, DC current added, AC current gain. DC current gain, AC current gain, common emitter terminal, common between base and collector. There's a transistor over here, and then a positive negative junction shields on the transistor. Input characteristic graph that's applied between the input voltage biased emitter, input with the current ampere bias, keeping output voltage current input voltage emitter as parameter characters similar to that with a forward bias diode. The current voltage bias emitter with the magnitude of base decrease with the increased voltage current collection emitter is because of the increased voltage collective effective base width, and hence with the recombination base current decrease. Output characteristic graph between the output voltage collection emitter by output current input ampere current, and keeping input current ampere bias as parameter. Active region. In regions of the junction emitter bias, the forward bias of the junction collection bias is reverse based with the output characteristic active of the region of non-horizontal lines because of the fixed volt value of the ampere base bias magnitude collecting current increases voltage collection emitter due to the effective since the leakage of the current is very small, ampere current is equal to beta ampere bias. Cutoff region. How both junctions of the reverse bias of the region of the ampere B ampere bias is equal to 0, but will be cut off the region of the ampere current with the ampere collector emitter leakage with the base open. Saturation region. Here both junctions forward bias by at least of the cut in voltage of current ampere current is independent with the ampere base. Collection emitter current amplification factor ratio. Output collector current input base or current DC current again. Current DC current gain, AC current gain between charge and whatever. We have ampere E plus IE plus IC plus IB. Ampere A is equal to IC over IE. Beta is equal to IC over IB. IC over A equals IC plus beta. Alpha equals beta over a plus 1 over 1 plus beta. Beta equals A alpha over 1 plus A. DC biasing. Biasing application external DC supply established fixed level. The current voltage transistor operates only at a particular point over the characteristics called operating point or Q point or quiescent point. So saturation active region Q, the quiescent point where the operating point is, and then over here we have voltage collection emitter and DC load little limit. Positive region. Type of biasing, fixed bias configuration, fixed bias emitter resistor, voltage divider bias configuration, collector feedback configuration, fixed bias configuration, simplest transistor, DC configuration using positive and negative transistor, DC analysis, capacitors are open circuit and shown in figure. A base emitter loop, applying the KVL, since VB and VCC are constant selection base from resistor sets the level of the base current of the operating point collector emitter loop. The base resistor controls ampere base and ampere collector. The level of the RC resistor capacity resistance capacity determines the magnitude of voltage collecting emitter. So voltage collector emitter equals voltage current collector over the minus voltage emitter minus voltage base emitter equal voltage base minus voltage emitter. Fixed base for the emitter resistor configuration contains emitter resistor improves stability over the fixed bias. Base emitter loop applying KVL. Voltage divided bias configuration. Previous qualifications of the question point with dependent on the beta, which for the temperature sensitive voltage divided base bias arrangement require the dependency on the OB beta. Exact analysis. Input side called the Thevenin equivalent circuit, with the Thevenin equivalent resistance is the input DC source is short circuited. The resistance Thevenin equation is equal to R1 times R2 E over R1 plus R2. The Thevenin equivalent voltage of the voltage constant current is returned to circuit voltage is given by the Thevenin equation drawn by the IBQ formula applying the KVL. By solving the output collector emitter by KVL, the collector feedback configuration improved the level stability obtained, providing feedback path. Base emitter loop applying KVL solving, we have collector emitter loop KVL solving, we have. Alright, field effects of transistors. Field effect transistors.